Today in this video we're going to talk about Likert and Rasch scales. And before we get started, if you haven't already looked at the scales brief in Moodle, then take a moment and go over that. Once you've done that, then take a moment, press pause, and read this abstract. Just kind of go over it so you get an idea of what we're talking about. Okay, today's talk is about the Brain Injury Vision Symptoms Survey, BIVSS. It's a self-administered survey, and it's about traumatic brain injury. So, let's look at the questionnaire itself for a moment. And there are 28 items. And you rate these items. You circle, you go through the questions, and you circle that, for example, distance vision blurred and not clear even with lenses, never, seldom, occasionally, frequently, or always. And you circle one of these answers. And then these are added up, and you get a total score as one of the measures. Now, we'll see in a moment that we create subscales out of this too, but this is ordinal data. Ordinal data means that 1 is greater, there's more symptoms with 1 than 0, more than 2 with, or more than 1, 4 is more than 0. You know, it's ordinal. But the difference between 0 and 1 is not necessarily the same as the difference between 3 and 4. And there are a lot of people that are very upset about people adding ordinal data. And but it's actually kind of a legitimate thing to do if you meet some assumptions. And one of the assumptions is that people's frequencies of these responses approximate a normal distribution. And it's been shown that summing them is okay in that context. The problem with ordinal data and scales is that these assumptions are not always tested. But in this paper we tested them. So let's talk about this. So there were 107 adult subjects that had TBIs, and they were self-reported TBIs, mild to moderate. And then we had reference subjects. The reference subjects were optometry students, first and third years. Now the first years, when they came for their orientation, they were given the test. And the third years actually took this test the week before their board exams in the spring. So we have these 3 groups. Now we later split the TBI into 2 groups and compared those adults who were similar in age as optometry students. So we talk a little bit about TBI here, and then we talk about the methods. 86 first years, 71 third years. 28 items, we've seen those. Now, the idea behind a scale is sometimes there's, like in the dry eye scale, or some scales that have just a few questions, each question is considered separately. But in most scales, bigger scales, they are considered more in total. So, for example, we could add up all the scores for the BIVs and get a single total score, but we're also going to break it down into subscales. Now, the idea of asking more than one question is, for a particular subscale, is that you are trying to get at an underlying latent variable. So, for example, maybe dry eye. You're going to a couple of questions that maybe is most characteristic by dry eye, or or tired eyes or something. So you're asking multiple questions to give a more reliable answer to this underlying attitude or scale or whatever we're talking about. So it's a linear relationship. That is, the idea is that it's a ascending or descending in a straight line, like we did with our regression. That sort of a concept. And when we talk about, we're going to talk about in a little bit factor analysis and see what we did with that. And in factor analysis, this underlying latent variable is a linear. The factors are linear, underlying, unobservable linear variables, and we talk about correlating each of the questions to those underlying variables. And some of the variables cluster with each other, and others do not, and are in a particular variable. So here we have, for example, the profile analysis for the Likert scale. And we see in this scale, we have this first set. So we have 8 factors. These 5 questions kind of clustered together. They were in the survey itself. They were question 24, 5, 6, 7, and 8. And we gave them kind of a common category name of reading. So short attention span, easily distracted when reading, difficulty or slowness with reading and writing. So the underlying factor that we can't observe directly is their reading ability. And these 5 questions, by asking multiple ones, we get a more reliable estimate of where a person falls along this subscale. We have another one, which is 5, 6, 7, and 8, which is comfort, eye discomfort, sore eyes, headaches, dizziness. And in this table over here, these numbers represent essentially the correlation of each of these questions with this theoretical, mathematically derived, unobservable latent variable that's here called factor 1, but refers to reading. And the second one refers to comfort. And you'll notice that these are all correlated with each other pretty well, but none of these other questions are correlated very well with this factor. And that's how factor analysis works. It finds questions that correlate highly with this underlying variable, factor, unobserved factor, and it correlates well between questions, or within questions, but not between the factors. That's the beauty of factor analysis. Very computer-intense analysis to find the combinations that work out this way. All right. So when we did this, we really only, when we were creating the factors, we looked at first-year students. Even though our sample had both first and third year students at TBI, we wanted the subscales to be a reference group for first years. And then we're comparing the groups against that. And a kind of a handy little way of creating scores. So we get a score for each of these factors. And the factors all have a mean are created with a mean of 0 and a standard deviation of 1. And so then we're able to look at differences between standard deviations. And basically, the analysis automatically computes our effect sizes, because effect sizes in terms of standard deviations, and the differences are in standard deviations. So with our Likert scale, we were able to make these subscales. Now, in the Rasch analysis, it's a little different. We don't just use the first years. In the Rasch analysis, we used all subjects, because the Rasch analysis, the Likert analysis just uses the test scores and what people's answers are. The Rasch analysis uses both the test scores and the questions related to the total test score and where the people fall on the dimension. So it's not only where questions fall along the dimension, but where subjects do as well. The Likert doesn't have that subject falling along the dimension kind of idea, other than it just gets, there is a scale and your total score says where you fall on that dimension, but it's not used in the fitting and the getting the weights for the various questions. And so it's a little different in that respect. The other thing is that the Rasch analysis and the Likert analysis too, for the subscales, everything is assumed to be underlying linear and unobservable. The Rasch scale, we could have done separate scales, but it turned out that given the general rules of thumb with Rasch analysis, a single underlying dimension was acceptable. So we created a bunch of dimensions with factor analysis for Likert, but we just used one underlying dimension with the Rasch analysis. The advantage of the subscales is we can make a profile analysis, so we can look at different people with TBI and see if there are different patterns of symptoms that are related to different types of TBI. In the Rasch analysis, you get one single score. Now, the advantage of the Rasch analysis is that you can go through and do an item analysis. All right. Let's step back for a moment and look at our Likert scale. These are, we came up with our 8 factors. We have in here first year optometry students, third year optometry students, and TBI patients. Now remember, these scores on the scale on the y-axis here, these are standard scores with respect to the mean reference of the first year optometry students. So overall, of all factors, the mean is 0. For each of the factors, when you factor it out, there will be some differences. Now, we can see that, for example, difficulty, slowness with reading and writing, not too big of a problem for either the first or third year students, but kind of a big problem for the TBI patients. Now, one thing, you see these little error bars. You'll find error bars very frequently, if not always, at least 90–95% of the time. There are error bars in graphs. Most of the time, the error bars represent either a single standard error, or sometimes there are 2 standard errors. In this case, well, if it's one standard error, the error bars may not overlap, but they're not significantly different. You can't really use overlap as a test of whether or not things are significant. If there are 2 standard errors, which is equivalent to a confidence interval, then they're going to overlap too often. And so I've developed what I call a Goldilocks Rule, where if you just use a single standard error, that's a 68% confidence interval. Remember, one standard, plus or minus one standard error, covers 68% of this theoretical set of means. It's too hot, and it says too many things are significant. 2 standard errors, on the other hand, are too far apart, they can overlap, and they would say something that is significant is not significant. So that's too cold. So 2 standard errors too cold, 1 standard error too hot. It turns out 84% confidence interval is just right. And so you can see that this standard error bar does not overlap either of these. So TBI is significantly higher than these two. Now, the 84% confidence interval is not usually shown in papers. That's something that I'm trying to get out there and suggest to people, because then you can just look at the overlap and see which values are significantly different, as opposed to having these complex little things around trying to explain what's different between groups that you're looking at. Here it's instant. And in this particular chart, since these are factor scores, and factor scores are in terms of standard deviation units, this is 1 standard deviation different from 0, this is 2. So you can see that the effect size here, the difference between this bar and these bars, is pretty close to 1.5 standard deviations. That's a really big difference. So an effect size of 1.5, same there. Now, here's an interesting one. These are the TBI patients, and remember, a higher score means more symptoms. Well, in the case of my eyes feel dry, they're really not different, or the TBIs are pretty close to significantly less dry feeling than even first-year students, although the difference between these two is more in the neighborhood of close to a half standard deviation. But third years, they're significantly different from both the TBI patients and these. They're that way on this measure, and also significantly different on double vision, which is really pretty interesting if you think about it. So these guys are taking their board exams. They're seeing double. They're studying so hard. They're seeing double. Their eyes are drying out. And so this turns out not to be a very good measure of TBI, dry eye and double vision. And in fact, in the Rasch analysis, when it went into its item analysis, it said these questions are not good for evaluating TBI and should be eliminated. So we see here, and you can tell really the biggest, most discriminating thing with TBI patients with this population is the question that says what looks straight ahead isn't always straight ahead. Optometry students, when they look straight ahead, they see things that are straight ahead. Not so much TBI patients. It's really significantly different, but more important, the effect size is like 6. So that's a huge, huge difference. With the, well, we'll skip this table for this week. The Rasch analysis looks at each question. This was what we were talking about eliminating questions. And it says these are z-scores on how much of an outlier each question is with respect to its scale. And we see that staring into space without blinking is not a very good question. Eyes feeling dry, not a good question. 5 standard deviations out. Eye discomfort, sore eyes, eye strain, not a good question. So the Rasch analysis does an item analysis that says, okay, some questions are good, some questions are not related to this one single underlying unobservable dimension. And here we have our Rasch statistic. The actual quantitative part is kind of an unusual metric, and it doesn't go from 0 to some high number, and these aren't even standard deviations. It's just different. but you can tell, whatever the metric is, that these are pretty big differences. All right. And I would like to just reinforce the brief's comment on, though, while it would be tempting to argue that this supports a diagnostic interpretation of Rasch score. In other words, if you get a score of 0 versus this minus negative number, or if you get a higher number, and this actually translates into a score of about 32 or greater for the Rasch analysis, going back to the Biv's original scale. If you get higher than a 32, then your symptoms, if you're a TBI, you're going to have symptoms up in that range. The problem is, it wouldn't be a good idea to use this as a diagnostic interpretation, because there are a lot of ways that you could have a lot of these symptoms. So you could score poorly on the Bivs, but not have a TBI. As an example, we can look at the questions in the CISS, the Convergence Insufficiency Symptom Score. And if we go down through, and my eyes feel tired when reading, also on a scale of never, infrequently, sometimes, fairly often, always, not exactly the same headings, but similar. Do you feel like you read slowly? There's a lot of similar things, but here we're talking about convergence insufficiency. So just like the TBI doesn't differentially diagnose TBI people, if you gave this test to TBI folks, they would do poorly too. So it doesn't. This test does not differentially diagnose how well you're doing. The usefulness of these scales is more in testing the effectiveness of treatment. So you would hope that you would do a little bit better in your treatment of people. So after they get a score, you treat them for a while, and then you test again. Their scores should get better if the treatment is effective. In this CISS paper, they have in here a Bland-Altman chart that we talked about in the brief. Here it is. And the mean of the symptom scores for CISS, 9 to 18-year-olds. And you can see that this is a retest, and it's pretty good. The 0 is a little bit higher on the second test, but not significantly, just doesn't hit exactly 0. So we wouldn't reject the null hypothesis with that. Similarly, with the Bivs, we have here some data that shows a test-retest. It's that while the Bivs has 28 items, we got rid of the ones related that tended to go towards those questions that weren't very good, and we left 25. So the Rasch analysis rejected 3 of the questions. We got rid of 3 of the questions and left us with a score of 25, and then looked at the total scores. And also that dotted line is very close and a little bit higher for the second test on that. But you can see some things to point out here. If we were to put a confidence interval around that dotted line, it would not. It would overlap 0, which means that the bias of the test is there's not a general bias of the second testing be higher or lower. One of the things that we're concerned about when we give a scale and then repeat it is that people practice, and then when they do it the second time, they think, oh, well, really I should have said this or that, and there is basically not a big bias in this. The other thing is the standard deviation for these differences. So this is the first administration of the Likert scales. This is the second minus the first. So these are the values. And the standard deviation of all of these is about 27. So what we're having, well, the standard deviation all the way across it. So the this range is showing 95% of the observations are falling about within plus or minus 27. That's 2 standard deviations above there. 2 standard deviations. So the confidence limits are 2 standard deviations above and below the 0. Not confidence limits, sorry, not confidence limits. Limits of agreement. Confidence limits refer to this mean line down here and its relationship to 0. Limits of agreement refers to these observations falling within, 95% of them falling within, say, about plus or minus 27. So we've talked about basically 2 types of scales. We've talked about Likert scales and Rasch scales. These are scales and they're methods of analyzing data that are ordinal in nature. The Rasch movement has come up because it's kind of a statistical heresy to talk about doing normal statistics on ordinal data because of that problem with the intervals. But at the end of the day, it turns out it doesn't really make that much difference. It can make a big difference in some settings, but I would argue that most settings, it really doesn't matter whether you do the Rasch analysis or the Likert. Now, the real advantage of the Rasch analysis is that it is very good at item analysis, and it allows you to find questions that don't match the primary underlying variable that you're looking at. Now, an error that occurs occasionally in the literature is people don't realize the assumption of Rasch that it's a single underlying variable, and they eliminate questions they say are bad questions, but they're just really questions that are on a different dimension. And so while they don't fit in a particular primary underlying latent variable that you're looking at, they could provide additional important information in a secondary or a second underlying dimension that could inform the clinician on some additional features. Not everything is in a simple one scale kind of environment. So we also talked about learning that we have to show that scales are valid. That means they test what they're supposed to test. We saw in this case that both the Rasch and the Likert did, in fact, were consistent in the higher. If you're just looking at TBI patients, the BIVs is going to be higher if you have TBI than if you're a normal patient. Now, you could also have some other problem like convergence insufficiency, but in general, it's a valid test in looking at that. And the other piece is reliability, and that's where we talked about the Bland-Altman charts, where we looked at the consistency from one test taking scenario to another. You want to give the test a couple of times, and if there's no change, you want to get the same answer. When you're treating a patient, I mean, you're kind of hoping that they get better, and you want that Bland-Altman chart to not have a 0 line, but you want it to be negative. They get better over time. In this case, there was the TBI patients for the periods that we looked at did not involve treatment, and so there was not an expectation of improvement or of non-improvement. They were consistent in getting their getting their scores. So that's scales. Thank you.